capital of Turkey that has been home to a range of different eras for centuries, transforming the nation's home into beauty. It is the harmony of the colors and designs from a combination of these periods that gives our collections their originality, form, and spirit. This has enabled our production and service to touch the lives of people living across 6 different continents. At Ketz, we harness our 100-year design and production experience to turn your lives into an elegant and comfortable experience. It all starts with an inspiration, one that comes from within life itself, from the heart of nature. What could be more important than realizing the dream of a talented designer, or witnessing your happiest moments while adding beauty and comfort to them? Each customer expectation is special, and so is each design. Thanks to our personalized and versatile design capabilities, we produce quick and effective solutions for your needs. Here in Ketz, a fully integrated production facility operates as a value chain designed for the sole purpose of maximizing customer satisfaction. A machine can only serve an idea, one that gives meaning to life. What makes us powerful is not the fact that we are the largest production facility in Europe, but that we're a strong strategic partner who can understand your expectations and help you realize your business goals. And our robust design and R&D department are the key to develop new and custom solutions to add value to your businesses. We are more extensive, more collaborative, and more responsive to your changing needs and expectations. Thanks to our excellent supply management and consistent quality, we're your reliable global partner who can offer timely solutions wherever you are in the world. In addition to our gorgeous upholstery fabric collections, we engage in other walks of life by designing and producing high-performance specialty fabrics for use in coaches, trains, airplanes, hospitals, and hotels. It is this thrilling journey that leads us to happiness together with millions of people around the world. Ketz, beauty and comfort.
Hedefimiz yüksek. Çünkü biz güvenin adıyız. Ortak yaşamı paylaştığımız alanların, yaşamayı arzu ettiğimiz hayatların, geleceğimizin daha güvenli olması için çıktık yola. 1977 yılında %100 yerli sermaye ile montaj ve bakım firması olarak başladığımız yolda, bugün asansör kapısı ve kabin üretiminin yanı sıra komple asansör sistemleriyle de hizmet veriyoruz. Hedefimiz yüksek. Çünkü biz modernliğin adıyız. Modern üretim teknolojilerini uygularken sizin için daha güvenli ve konforlu alanlar üretmek için çalıştık. Azimle daha yükseğe. Üretim, yönetim ve satış ekibinin yanı sıra Ar-Ge departmanımızla inovasyonu sağlarken dikey ulaşım araçlarını 30.000 metrekarelik üretim sahamızda yıllık 100.000 otomatik kapı, 5.000 kabin üretimi ve özel çözümlerimizi tecrübeli kadromuzla hızla gelişen dünyanın hizmetine sunuyoruz. Hedefimiz yüksek. Çünkü biz konforun adıyız. Teknolojik yatırımları yenilikçi ve sürdürülebilir ürünlere dönüştürüyoruz. Hedefimiz yüksek. Çünkü biz geleceğin adıyız. Ülkemizde sektöre olan katkılarımızı 1998 yılından bugüne Atik ve 2008 yılından bugüne Altes asansörle duyururken, komple asansör sistemleri ihracatı için kurduğumuz Mars Elevator'la uluslararası bir marka olma yolunda emin adımlarla ilerliyor, hem sektör hem de ülke gelişimine katkı sağlıyoruz. 5 kıtada 60'tan fazla ülkeye ihracat yapıyor, dünya pazarına Türk asansör sektörünün komponent imalatındaki gücünü gösteriyoruz.
We imagined a fabric that can be used in every aspect of life. And we made it. Madeline. Madeline by Mogul.
Tomorrow, the sun will rise again. Tomorrow, the earth will offer us its generosity. Tomorrow, life will go on. Yet tomorrow will not be the same as today. The damage we have inflicted upon our old earth is unfortunately irreversible. Even a small PET bottle consumed daily takes centuries to break down in nature. Exporting from Turkey to more than 30 countries, Polytex produces recycled yarn under the brand Polyeco with the environment in mind. It takes the flakes created by breaking down PET bottles picked from the waste collected, processes them, and obtains chips, the raw material for polyester yarn. With these chips, through different production processes, Polytex produces Polyeco, 100% recycled polyester yarn. Polyeco products have the GRS certificate accepted worldwide. The journey that began with PET bottles turns into a success story of the textile industry. In this journey, through the recycling of PET bottles, natural resources are preserved, industrial processing reduced, and water saved. In this manner, we do not waste the future. Polytex, Polyeco.
Do you hear us? Professor Pouردeyhimi, do you hear us?
All right, I can hear you now. Yes, thank you.
Oh, great. Great to hear from you. Okay. Welcome to today's second session. The first invited speech is Professor Pouردeyhimi from North Carolina State University. His speech is about promising materials.
All right, shall I go ahead and start? All right, can you hear me okay? Yes, hello, can you hear me okay?
I can, Behnam, from here.
Yeah, I can't hear anybody over there. I don't know what's going on.
I can hear too.
All right, so am I in the full screen mode?
Yes, Professor, it's full screen.
All right, thank you. So I'll go ahead and start. Good afternoon. I'm sorry I can't be there with you and have to do this remotely. I want to credit my former student, Dr. Hamid Ibrahimi, who did the bulk of the work here, and he's now with Eastman Chemical. The National Academies is really a big deal in the US. We have the National Academy for Sciences, Engineering, and Medicine. They had a committee that worked on grand challenges and opportunities for environmental engineering for the 21st century. And as part of that, they were really focusing on designing a future without pollution or waste. Essentially, the report starts by talking about the model that we have, the linear model of take, make, dispose, in terms of how we make products, and that leads to affordable products for everyone, but it also generates billions of tons of discarded products and byproducts. And it uses a great deal of energy and resources that are never recaptured. What's of note is that in high-income countries, a lot of the materials and resources that we use are turned back into the environment as a waste stream within a year. And so this was their opening statement, and they had a lot of really interesting recommendations in terms of what needs to happen, and I will share some of that with you. We are, of course, all familiar with these pictures, especially when they end up in the front page of the National Geographics. It takes the attention of the legislators, and they come up with policies and decisions without looking at the consequences of those decisions. But the fact is that we do have a problem. Many of the waste materials that you see are actually packaging materials. And of course, the solid waste is expected to triple by the year 2100. And of course, the National Academies focuses on the less consumption, product design and manufacturing that minimizes waste, focusing on recycling and reuse of materials, and then preserving really resources for the future. The model that they came up with is really interesting because it's a holistic approach that really starts by designing for resource efficiency. So you start with the end in mind in terms of the product that you're designing, and you take into account all of those factors. You design them for example, recyclability, for easy disassembly, for repair, for longevity and reuse. And then, of course, you have to really look at all of the things that go into your manufacturing, from your sourcing, from your manufacturing, your distribution, how you use it, how you recycle it. And then you really have to look at what ends up in the landfill. And so what they're really talking about is a new approach to design products that's based on life cycle thinking. And I do know that some people have started moving in that direction and trying to redesign some of the existing products, but obviously this is going to take a lot of challenge for it to come about. The recommendations that they had are very simple. Redesign products in terms of the production processes, and make sure that you have a more resource efficient process, that you reuse, repair, recycle, and minimize pollution. You have to look at the consequences of what you do in terms of the life cycle analysis and the cost benefits of alternative approaches. You have to quantify the waste stream characteristics and see how you can perhaps reuse or recover some of those materials. Identify other products that could be manufactured and reused and recycled that would have a lower cost, lower emissions, and less energy. And really develop a new resource recovery technology that would allow us to have processes that are cost effective for handling the waste stream and the materials that we deal with. Our vision within NWI and our broader group of colleagues that we work together is really looking at sustainability in different forms, from the polymerization, that's a term that my colleague, Dr. Jan Genzer coined, but really looking at your classical recycling as well as chemical and somatic, looking at upcycling, looking at various types of polymer modifications and energy recovery. In terms of product sustainability, really looking at new materials, cellulosic materials, blends of materials, and you're designing these again for recovery and reuse. Now, these bring out challenges because the current systems that we have, processing technologies that we have, are designed around classical polymers such as polypropylene, polyethylene, polyesters, and nylons. And once you move to these new materials, you really have to take a step back and see how you can essentially design these processes to ensure that the material can be processed easily. Last but not least, you have to really look at the environmental impact, develop metrics, develop definitions for biodegradability, which we don't really have today, look at the end-of-life management, litter control, and then, of course, you have to engage the infrastructures and municipalities and also look at human behavior as part of that. I'm going to focus this morning on the polymer sustainability because that's what the talk is all about. And so biopolymers offer significant opportunities for creating new opportunities. But of course, there are many challenges, and these challenges have to do with the transformation of the renewable resources, and they have to be cost efficient. Current materials are not cost effective. Sustainable problem materials must have similar or improved properties compared to the traditional materials that you're trying to replace. That is not true today. And you, of course, have to look at the entire life cycle analysis to make sure that you look at the consequence of such things as diverting raw materials that are used, for example, for food production into polymer production. There's been a lot of debate about PLA and diverting corn from a food source to polymers. And so you have to look at all of these consequences. If you look at biopolymers, there's a lot of them, and you can put them in different buckets. The ones that are made from biomass, so the polysaccharides and pectins and lignins. Now, most of these really not fiber-forming polymers, and so while they're interesting for the bulk of materials that we use, they're really not readily available for us to use. You have other biopolymers that are produced by microorganisms. So these are all the PHA and PHP and PHBH and PHPV and all the family of the PHAs. These are wonderful materials in terms of their marine biodegradability. However, they're in short supply. They don't really have the melt strength. They don't have the filament spinning characteristics, and they're unbelievably expensive today, and they're in short supply. Then you look at the ones that are synthesized from other monomers, the polylactides, and the PLA is a good example of that. So PLA is pretty much available in large supply, and that's part of the reason that we're focusing on that. Then you look at other materials that are made from petrochemicals. So these are things like your PCl, your PBS, and other types of materials that could be potentially used. So when you look at the portfolio of materials that we have available today, we have a very limited choice in terms of fiber extrusion and making products that would go into fibers and nonwovens. And so PLA is probably the only one that could work today. If you look at biopolymers today, they're primarily used in packaging materials. If you look at textiles, it's less than 5%. Nonwovens is a very small percentage as well. And so primarily they go into processes that are less, a lot more forgiving than the fiber spinning. So if you look at injection molding and creating films, that are a lot easier to do than fiber formation. So the lowest hanging fruits for them has been packaging, and that's where they have focused primarily. So all of the consumer goods that we have are less than 10%. And of course, that really presents a great opportunity because many of the consumer products end up in the waste stream. We also have to look at it from the greenhouse gases that we generate. So if you look at the carbon footprint of some classical materials, polypropylene is pretty low. PLA is actually really ultra low. But most of the bulk of the materials that we use in the nonwovens are less than 2. And that's really important because if you put it in perspective, they're pretty low in terms of their carbon footprint. But you also have to look at water consumption. You can't look at just one dimension. And of course, water could be processed water, cooling water, and then in the case of using a corn product, for example, irrigation water as well. So if you look at NGO, which is the PLA, and polypropylene and polyethylenes that we would use, still represent the lowest water consumption of all the other materials that are presently available. And so what we use today is not necessarily really bad in terms of its carbon footprint, but however, depending on how they're disposed of, they could create challenges in the environment. So when we look at biopolymers, you really have to answer some questions. What's the end of life? More importantly, do they process an existing equipment? And the answer to that is often no. Do they process at the same speed, at the same throughput? And oftentimes the answer is no. Do they produce similar products? And the answer is often no. And do they cost the same? And of course, not today. And then what's really important is that are they available in large volumes once you start looking at some of the consumer products? And the answer is the only one that's really available in significant volume today is PLA. Many of the other biopolymers are not available in large quantities. And of course, when we look at nonwovens, they're not made from one component, so they're typically bicomponent, and of course that aggravates the problem. The machinery is not available or suitable for processing these biopolymers. They are not easy to process, and they don't really create new products. So we have a lot of challenges that we have to face. So when you look at what's available today, the materials that we use are really expensive, and the question is, will the consumer be willing to pay for an expensive bio-based solution? And oftentimes the answer is no. Carbon footprint of PP is pretty low. So will we be able to really replace PP with another material that has a similar carbon footprint? And of course, in many of the products that we use in nonwovens today, they're incinerated. And so that may not be an issue at all in terms of the environmental challenges. So when you look at PLA being really the only option, It's available in large supply. It has a pretty good carbon footprint. It has a good history. But PLA has a lot of challenges. And of course, PLA is a generic term that we use. There is no such thing as PLA. You have two isomers. You have the L and the D. So these are either PLLA or PDLA. So NatureWorks products are primarily PLLA, maybe with a little bit of D added. And then Total Corbion is primarily PDLA. So what we are referring to in this presentation is really mostly PLLA because it's a lower cost, it's easier to produce, it's available in large supplies. And that's why one of the reasons that we focused on that with respect to this research. So if you look at the challenges, PLA has low crystallinity. It's a pretty brittle material. It has low strain at break. It cold crystallizes. If it's not crystallized properly during the process, it continues to crystallize and it becomes even more brittle. It has a lower softening temperature. So this is your heat distortion temperature or heat deflection temperature. But in terms of the pros, it's got a pretty good tensile strength. It's a renewable resource. It's biodegradable. It is not home compostable. It is industrially compostable. And it also has a lower carbon footprint. So there are challenges that we have to face, and the work has been focusing on optimizing those challenges. Now, we use polymer blends, and I'm going to give you just a glimpse of what we have done in the work that Hamid carried on for about 4 years. We did not want to use plasticizers and other additives that could essentially render the biodegradability ineffective. So we're using other biopolymers. So we're taking the classical 6100D, which is the crystalline version of the PLLA, and adding PBS, two different versions of PBS, and adding PLA. And so the reason we do that is that there is some literature that hinted at PBS and PDLA acting as nucleating agents for PLA. PLA has a very, very low crystallization rate, which creates many challenges. Its total crystallinity is low, its glass transition is low, its heat deflection is low. And so the intent was to really see if we can improve these by just using polymer blends. And of course, the polymer rheology and the immiscibility of these materials would make a challenge in terms of the filament spinning, but I'll share with you what we've done. So the graph on the left just shows you the D content. So on the 0, it's a pure PLLA, 100% is pure PDLA. And what's interesting, when you start adding a little bit of D, you notice that the melting point drops very significantly. And so this is actually an opportunity because when we use a sheet core structure in nonwovens, we could essentially do that and create a lower melting sheet that would be facilitating really bonding a lot better than we do today. And of course, if you look at the crystallinity, it also impacts your crystallinity, it impacts all of the various properties. At some condition, you might get a stereocomplex. And if you take the PLA and PDLA, especially at about a 50-50 ratio, you would form a stereocomplex. And this becomes a very high melting point, high heat resistant PLA. We haven't been able to really demonstrate that in the fiber form, but we've demonstrated it in other forms. And so if you want to do this with fibers, you require very significant post-processing and annealing conditions to facilitate that. But once you start adding these polymers, your thermal properties, you change, your rheology changes. And so you have to be conscious of what you're doing with these materials. These materials are not miscible. So you can look at these blends. You can see the large particle sizes of these. Of course, if you go to very low amounts, it doesn't really impact your melt strength of the polymer. But if you go to higher amounts, you would have an issue. With filament spinning, you're probably limited to about 12.5% of addition of, say, PBS in PLLA. And beyond that, you would get breaks in the structure. And so I'm going to show you two videos here. So you notice one, the fiber is extruding really nicely. The other one is dripping. And so this is a case where if you go to higher levels of these biopolymer additives, then you're not going to be able to actually spin these materials. When you add PBS to PLLA, it actually enhances its crystallinity. It shows you basically as a function of percentage. So once you get to 10%, you've improved the crystallinity very significantly. You've gone from something like 32% to over 55%. And then, of course, you look at the mechanical properties of these materials, you get a really different range of behavior. PBS is pretty ductile, PLA is pretty brittle. So when you start adding these, you're actually making the PLA composite a little bit more ductile. And if you look at PBS by itself, a very, very high elongation to break, but its modulus is lower, obviously, because of that. So let's look at the crystallization of these materials. So if you look at PLA by itself, and I'm going to accelerate these. So this one is accelerated, and it takes an awful lot of time for the material to crystallize. And this is a post-treatment process on fibers. So these are fibers that you're looking at actually, and incredibly slow. Now, when you start adding additives to these, the magic happens. So if you look at the PLA, PDLA is already done. The PBS is still going, and the PLA will go forever. But of course, you also are changing the crystalline structure of these materials. So you have lots of little crystals. You have more crystals here, but larger crystals. And so these are truly acting as nucleating agents. And that's really good for many reasons, because especially in thermal bonding of nonwovens, we really like small imperfect crystals because that facilitates your bonding at a lower temperature, and of course a higher crystallization rate means that you have a higher reptation, and that means better chain entanglement at the bond spot, and you get a better performance in the material. We were interested in heat deflection temperature. You can, of course, measure it if you had a block of material using your classical 3-point bend test, but we're using a DMA. And actually, with the DMA, you can essentially see what really happens right about here. And so based on that, you can predict the heat deflection temperature of these materials. So this is actually a really important graph because it's looking at two very different scenarios. So the as-spun fiber in this case is really a partially oriented fiber. And so these would be for things that are, for example, moldable. So moldable structures, these would be very, very important. Think of these coffee capsules and automotive products that need to be molded. And if you look at the PLA by itself, if you look at the black is crystallinity, you're less than 40% crystallinity, but you have more than 40% shrinkage. And the softening temperature is roughly about 63, 64 degrees. So these are the challenges that you have with PLA, which is partially oriented. Once you start adding a little bit of PBS, your shrinkage goes down to essentially zero. You have a higher crystallinity, but note, the softening temperature is now almost 76, 77 degrees. And so your heat deflection temperature has gone up very, very tremendously. When you look at the PDLA, it doesn't really add much. It doesn't improve the softening temperature, doesn't improve the shrinkage, and it actually reduces the crystallinity. And if you know that you had lots of little crystals, but you have actually a total crystallinity would be lower. When you look at fully drawn fibers, the story changes. So if you had a fully drawn fiber, the PLA by itself is now almost 60% crystalline. Its shrinkage is about 5%, and its heat deflection temperature is still about 68, 70 degrees. It's still low for many applications. If you put it especially in a hot aqueous environment, that would be a major challenge. When you add a little bit of PBS to it, your crystallinity increases, your shrinkage actually reduces to about 3%, your heat deflection temperature goes up to over 85 degrees. And when you add the PDLA, you get also a similar behavior, except your crystallinity is a little bit lower. But I also want to note that sometimes we actually like smaller crystals. So for example, for filtration, we like smaller crystals and lots of them, because, for example, we trap charge inside the defects within the structure. So for the drawn fibers, you actually have two options. You can use either PBS or PDLA. And really for partially drawn fibers, you have no choice. You have to use PBS. And it impacts the performance very, very significantly. And then what this means is that a lot of the challenges that we've had with these materials really go away by just doing some very simple blends. So if you look at the summary of what I presented, PBS, adding small amounts of PBS eliminates shrinkage in both spun and drawn fibers. It enhances the softening or heat deflection or heat distortion temperature in both undrawn or partially drawn and fully drawn fibers. It eliminates essentially shrinkage and increases crystallinity very significantly. And more importantly, it actually eliminates that cold crystallization that happens with the pure PLA. And when you look at the addition of the PDLA, it's really more significant for fully drawn fibers and increases the crystallinity, but you have lots of smaller crystals. It also enhances your softening temperature significantly, very similar to PBS. And then it really doesn't impact the shrinkage as much. It's for fully drawn fibers, but you have two pathways that we could use without really resorting to anything else. And what's also really interesting is that you don't even have to pre-compound these. So you could essentially feed these polymers at the throat of the extruder without compounding them. And the extruders are typically long enough that you get enough mixing, and that reduces the challenge of having to pre-compound these and eliminates some extra costs. All right, with that, I want to stop and acknowledge the companies who supported us in this project, and especially Hamid Ibrahimi, who is at Eastman Chemical now, and colleagues from NatureWorks who mentored and supported Hamid and actually provided some of their equipment, analytical equipment for us to be able to do what we did. And with that, I want to stop and see if there are any questions.
Thank you, Professor Pourdeyhimi, for this nice presentation of the polylactic acid. Is there any question coming from side? Yes. Behnam, Ali is here. Thank you very much for having you here, and nice to see you again. I appreciate your presentation, but I would like to see once more this spot stage microscopy and see the development of crystal size. How did you manage that, and how can you repeat what it says?
Yeah, so actually it's a really interesting microscope. It's a polarizing light microscope with a heat at the stage. So with fibers, we could essentially do post-heat treatment and do it before and after. But then with this technique, you can actually see the entire crystallization kinetic and how it happens.
Is there another question? Just
Dr. Pourdeyhimi, this is Yusuf.
Hello, Yusuf. How are you?
I am fine. How do you overcome this problem of recycling in the United States? Which methods that you are using generally? Yeah,
so I think we are moving slow in that direction. This culture is a little bit different. So recycling is happening in a lot of different places. And of course, if you look at the easiest thing to start with were the water bottles. And so there's a lot of products that are made with polyesters that are made from water bottles. There's a company in South Carolina that produces about 100 million pounds of recycled nylon and polyester from carpets, and they've managed to actually figure out the process. There are many challenges because, when you take the carpet fibers, they really have calcium carbonate, they have a lot of other things. And then, they use chain extenders, they use a lot of other compatibilizers. If you buy a Ford truck today in the US, 90% of all the plastics that are used actually are recycled from carpets and other materials. So there's a lot of that happening. It's not happening enough, but there's a lot happening. Eastman Chemical announced a very large endeavor on chemical recycling of PET, and so that's happening. So there's a lot of activity. One thing we do not have in the US are really the ability to do industrial composting, and which is really where a lot of these biopolymers need to be. Now, if you go to Canada, they have hundreds and thousands of industrial composting facilities. So Canada is really focusing on biopolymers that could be industrially composted, whereas here we're really looking at mechanical recycling, chemical recycling, And so these biopolymers would end up in the waste stream like other plastics. And actually, they would probably create a challenge because, to sort them is going to be an interesting challenge. So there's a trend now that instead of having one recycling bin, you would have multiple recycling bins. So you could actually separate things ahead of time because, the recycling facilities, it would be pretty hard for them to do so. So it's happening, but it's happening slowly.
Thank you very much for the explanation. How do you keep up, so young, over that age?
I'm sorry, Yusuf, I didn't hear the question well.
It was not a question, actually. How do you keep your shape? You look so young.
Because I had really good students.
Thank you again for joining us from the United States. Online. Okay, there is one online question.
Thank you.
What do you think about the future of petroleum-based polymers? The question is coming from Fatih Soari, Uludağ University.
I'm sorry.
Do you hear me? The question is, what do you think about the future of petroleum-based polymers?
Right. So I think, look, if you look at petroleum-based polymers, so if you look at, say, medical products that we use today in the US, and I think some of the same trend is happening elsewhere, they're not trashed. So they're incinerated. And if you look at, these polyolefins, you only have carbon and hydrogen. So they're perfect fuels. So I think, there's going to be products that you can't really replace easily. If you look at all of the processes that we have, the melt-blown process, the spun-bond process, they're really all designed around polypropylene and a little bit around polyethylene. These materials have a long history. There's a lot of different grades available. And really, if you take an existing polymer, just put it in there, it's not going to work. And we're not going to go back to the old cotton polyurethane medical gowns because that's not going to happen. So I think there are certain categories of products that I don't think you're going to be able to replace. There are other categories that could easily be replaced. So, a good example is wipes. There's no reason why we can't really reinvent the wipes, especially the consumer wipes, to make them a little bit more sustainable. And that requires really taking a step back and looking at perhaps new processes, new technologies. If I had to predict, most of the wipes today are carded and then hydroentangled. I think people are probably going to start moving away from that, and they're going to go to like a wet laid system where you can essentially take different sorts of cellulose. The wet laid system is a lot more forgiving. And so I think some of that is already happening. But I think in some of the classical areas, I don't think the petrochemicals are going to go away.
Thank you. Thank you again for joining us and replying our questions. Once again, we hope we could meet you again on another conference. Thank you very much. Our second presentation is from Professor Saad. He is joining us again from North Carolina State University. This is the second invited speech. His topic is creating multifunctional materials, platforms from textiles and fibers from superhydrophobic surfaces to enhance food security and cost sorption. Okay, the stage is yours, Professor Han. Thank you very much.
I need access to screen sharing.
Just a second.
Okay. Got it.
Okay. You see?
Yeah, can you guys see?
Yes, we could hear you very well. Please.
Okay, all right, so thank you for giving me the opportunity to be here there virtually. Thank you, the organizers, for allowing me to talk. I guess we're going to have a second NC State talk. So I will try to go a little bit more nitty-gritty details on a few topics, as you will see. But I should mention that my interest in fibers and textiles really originated from Dr. Pourdeihimi. He's the one several years ago, I was walking in the College of Textiles, and he said, "Hey, Saad, let's talk." And he's the one who kind of inspired me in looking into this area, which has become a fertile area for me in my research group. So what I want to do today is talk about three stories, and I'm going to present some overview of each without going into too much details. First, we are going to look at fibers, and in this case, we are going to look at natural fibers derived from trees. And I'll show how these fibers are used in enhancing food security. Then we are going to take these fibers and modify it and actually try to make it a little more applicable to advanced applications and by impregnating them with metal or organic framework. And then finally, I'll switch topics a little bit and actually talk about coated fabric. So this is where the textiles angle will be more kosher. And so if you look at it, we start with substrate, we modify the substrate, and then we look at a coated substrate. The first two will be the same material, but this one here will be a little bit different. So let me start off by talking about story one. And the story one really originates from a grand challenge globally to enhance food security or food yield in various countries, US and abroad. Our focus has been more abroad, particularly looking at sub-Saharan Africa. The idea here is that many of the food that we develop or grow is lost because of insects and worms. So here's a picture of a nematode, which can go and create damage to the plants in various aspects, from the seeds to the roots and so forth. And so traditional approach for this in most countries, including the US, is to spray and overspray. And you can do that manually, you can do that through an airplane. And when you do that, what you have is you lose 80% of these sprays in the environment. Most of these sprays goes to the soil without affecting the product. And so there is a need for a more localized delivery of what we call active ingredients. So the active ingredients would be the pesticides and the nematicides. So I'll give you a couple of examples where this becomes very handy. If you go to Africa and you look at Benin, which is a small country in the western side, and other countries in the western side, one of the major crops is yam, and a lot of these crops are being destroyed by nematodes or insects coming in and destroying it. If you go to the right-hand side of the plot, or Africa, or the Eastern Africa, you have places like Kenya and Tanzania, where 80% of the crop is lost, and one of the staple crops there is potatoes. So there is a room to develop new technologies to enhance this. And what we have been doing is a very simple approach. We are actually taking plants, and shown here is a picture of a banana plant, and we are then creating fibers. And these fibers are then made into papers. The papers are impregnated with a biopesticide, and then the farmers in Africa then take this paper, wrap it around seeds, and plant it. And that's why it's referred to as a wrap and plant approach. So here we're using a natural fiber, no chemicals involved except the biopesticide that we are putting. So why banana? The banana is abundantly available, it's low cost. And one of the interesting features of banana is this tubular structure, which enables it to retain moisture, as well as provide some accessibility to the cargo, for example, the active ingredients. And what happens is the banana have the right ratio of cellulose to lignin, and these are useful in binding the active ingredients like the biopesticides and the nematicides, and providing the proper release. So Here we are dealing with then banana fibers, and the approach we take again is we get these banana trees, and these are waste materials. So bananas, once the banana happens, the tree is waste. So you take them, we crush the fibers, we actually mix it sometimes with corrugated cardboard, so it has some aspects in terms of recyclability. In the lab, we would make a slurry, we would put it and dewater it, and out comes these banana sheets. So this is what happens in the lab scale, and we can change the structure and the morphology of these by beating the fiber to a different extent. If you want to go large scale, we can actually go to large scale. This is a paper making machine in actually at NC State, and it can actually produce a large quantity of paper, believe it or not. And typically this involves the same thing as the lab scale. We make a slurry, we put it through rollers, and as it's going through rollers, we take the moisture off, and we dry it using multiple stages, and eventually we roll it into the papers. And these papers is something that we can then give it to the farmers who are involved in Africa. So we have actually about 80 field trials that have taken place in Africa, in different countries of Africa. And this is a picture of some of the farmers taking and putting and wrapping yam seedlings and planting them. And these are some of the yams that have been grown from using our approach. So again, so we are using very simple approach. We are taking natural fibers, not yet a textile, and making paper out of them and using that as a way to enhance food security or crop protection. The question is, does this work? So this is a busy slide, so let me show you some results from field trials. So if you look on the right-hand side of the screen, shown here is the potato yield in Kenya for 2 different years. We have other years too. So here is the yield without any modification to the farmer's approach. On the right-hand side is the yield where we have the paper impregnated with abamectin, which is a biopesticide. And you can see that the yield has gone up by a factor of 3 or more. So that's a good sign, and that has made the farmers quite happy. Now the next step would be to try and implement it in a more commercial way. If you look at the population of the nematodes, and they're referred to as juvenile, you want the nematode to decrease. So this is the way the farmers work, and you can see that they have a certain number of nematodes. But when we use our approach, then the nematode hatching or the nematode population goes down. So that also is useful here. So that's what's happening in the potato area. And again, these are showing you some diseased potatoes. We see you have to zoom in to see it. On the left-hand side is yam production. So what we see here is the reproduction of the nematode. So what you want is that you want less or fewer nematodes. So if you're just focusing on one color, let's say the orange one, you see a certain number of reproduction of the nematodes. You want that to go down, and which we see is that as you use our technology, it actually goes down. And you can see that for different field trials taking place in different years. So in the yam also, we see some significant changes. The nematode population goes down. And actually, the bottom left-hand side, you can see that the profit margin for the farmers tend to go up also. So there's been some significant benefit using this very simple approach. And my colleagues in Kenya actually did some cost-benefit analysis to show that the way things were going, and this is for potatoes, is that actually the farmers were losing money and reverting to doing something different. But then with the approach, you can actually, the farmers have started to make money. So this is actually a fairly good approach. The cost-wise, it's relatively low cost. There are some issues that needs to be resolved to make it a very commercially viable approach, but this is something that has taken place, and the farmer seems to be quite happy. And so now we can now take and modify this approach for other countries, including Europe, Asia, and the US in other ways. So that is the first story, which is using banana paper or taking banana fibers and creating something that's useful in agriculture to enhance the yield of food production. Now, why does it work? Well, there's some hypotheses, one of which is that when you have these banana paper wrapping the seedling, whenever you have a plant, any plant sends out signals to the worms or nematodes to come and attack the plant. These are referred to as root exudate. And what we believe is that the banana paper prevents the signal or messaging to go to the nematodes. The second could be that there's a physical absorption, a mobility of these exudates. So you have a lower exudate. So that's why so the nematodes sees few of them. And the third is just a physical barrier for the nematodes to go through that paper wrap. So these are some hypotheses that has been come up with our colleagues in Kenya. One or both of these, or all of these probably work in our favor to make this a useful approach for enhancing food production. So we have the banana paper or the fiber, and we see that it works. Now, what else can we do with it? So that's the second story. Can we use banana paper beyond agriculture? And so my student and postdoc actually came up with the idea that let's make some banana metal organic framework composites. So many of you may be familiar with MOF, as they refer to the organic inorganic hybrids. And there are many types of MOFs present, and they're given different names like ZIF and MIL and UI and so forth. The beauty of the MOF is that they have very high surface area, and they're structurally flexible, and there are many kinds of MOFs. And the high surface area is what tends to have researchers gravitate towards MOF, because it can be used for capturing gases or neurotoxins or other moieties, VOCs and so forth. And so there is a lot of work going on in trying to get MOF. And most of these work are going on where they're using synthetic polymer substrate. So there are two things what we wanted to do. We wanted to see if we can replace this synthetic polymer substrate with banana paper. And the other is to try, many of these approaches use a lot of chemicals. If we can avoid some of these, at least minimize or get it to be a lower extent of using chemicals to produce these composites. So why banana paper MOF composites? Again, we are going into natural material which are used from waste, and these are lignocellulosics. We have tunable porosity and strength, and that presumably will help us get into a higher loading of MOF, easy diffusion of gases if you want to capture gases. These lignocellulosics seems to have good mechanical strength and flexibility, and then we would avoid using harsh chemicals, or not avoid, but probably use less of them. This is a picture of a banana paper where MOF has been deposited. I'm showing ahead of time, and we have used a zinc-based MOF referred to as ZIF, and you can see this is a cross section that the MOF is well in there, not only on the outside but inside as well. And so here has a nice coverage of MOF in these banana paper composites. And so the MOF we have used is ZIF, and we have used, there are many ways of adding MOF. We have used the vapor phase approach, although there are many other approaches there. And so the way we have done this is the following. We take our banana papers, the same banana paper which is helping us improving crop yield in Africa. This is the cross section. We'll do atomic layer deposition on it, and then with zinc oxide. And then what we do is we then put some vapor of the MOF precursor, and at a certain temperature, and out comes the banana paper with the MOF impregnated in it. So it's a vapor-based treatment, although there are other approaches that can be done. And when you do that, what you see is that the beauty is not only the structure of the banana paper, but the many functional groups that the banana paper have makes it very conducive to grow things on it. And so we can, when you use the zinc oxide for ALD, we can easily have the zinc associated with it, and then we grow MOF, the MOF can go on the zinc to give the banana paper MOF things there. So we're taking advantage of two things, a couple of things. First is it's a natural material. It has a nice porous structure, and third, it offers a lot of functionality to do functional treatment and get the product that we want. So the question is, does it work, and how well does it work? So I'm going to show you some results without going into detail. So first one here is showing you CO2 absorption. This is just for pure banana paper, and this is for banana paper with MOF. One of the things I want to point out is that the absorption we are getting is in the same range, or and almost the same as what we get with pure diff or the pure MOF. This is suggesting that we are not in any way impeding the efficacy of MOF. So that's good. That's suggesting that the MOFs are not getting blocked or anyway, and perhaps the banana paper structure is helping that. Second is actually a mixture of carbon dioxide and nitrogen, and we see that we have good absorption. And we actually see that the absorption goes down with temperature, suggesting the mechanism that being an exothermic process. The numbers are pretty good. So again, it's a viable approach. And if you look at the cycling of that, we can do some nice cycling with temperature, the reversibility. So seems to show some good properties when we try to do CO2 absorption, just pure CO2 or CO2 from a flue gas. The other thing what we can do is look at antibacterial efficiency. So here is a control, and you can see when we grow E. coli, it seems to grow. And even with banana paper, it seems to go, but when you have banana paper MOF, you actually, within an hour, you actually start disintegrating or killing the bacteria. That's shown here more quantitatively. This is after 1 hour, you can see very little bacteria left, and after 3, 8, and 24 hours, there's hardly any there. So 99% of the bacteria are gone in the first hour. Now, I should point out that there are work done using MOF and with a substrate for antibacterial, but many of these work actually use an UV exposure, so we don't have to use that. So that's an advantage there as well. So that's one functionality. And one other is a mechanical property. So this is a polypropylene with MOF. And when you do is when we grow polypropylene, MOF on polypropylene, you can see mats. It is not very strong. You use the banana paper, you can see that it can bend, it can twist, and it doesn't break. So we do have we have a better or more resilient material. The Young's modulus or the strength does not change, suggesting that when we grow them off, the banana paper integrity is retained. And perhaps one interesting thing is we've tried to show here surface area versus tensile strength. And what we find is that we get the best of both worlds when we use banana paper MOF. We get good tensile strength. We also have good surface area. So it's a very nice compromise when you're trying to use these features as well. One other property that I do not mention today is we can actually use these as a sensor for looking at VOC components. And we are doing that with our colleague to look at VOCs that are coming out of plants. So we can then capture plant disease before it starts to show up in plants. So that took care of the second story. And then what I want to end with the last one, which is somewhat different. So we are switching gears here. So we have talked about fibers, natural fibers, used by itself, then modified to impregnate the MOF. Now we are actually going to coat a substrate, and the substrate that I will share results with is cotton. And this is some company came to us and said they wanted some robust coating, which are super hydrophobic, but fluorine free, and they wanted a waterborne type coating. So we thought of taking advantage of the hierarchical structures to develop these coatings. And we wanted to, and we played around, and the approach we took is a block copolymer approach. So the idea would be that we would have block copolymers of hydrophilic and hydrophobic moieties. And the hydrophobic segments would add to the surface roughness and the hydrophobicity. The hydrophilic segment would provide some adhesion to the textile substrates, and presumably by changing the amount of hydrophobicity and hydrophilic components, we can create formulations with the best world, or we can do maybe multiple coatings and so forth. So that's the approach we took, and that's what I'm going to share some of the results with in the next few minutes. So we did a very simple approach. We took PDMS, which would be the hydrophobic moiety. It is flexible, and hydrophobic. The problem is that it lacks some of the mechanical properties that you want. And so the other moiety would we have in the block copolymer would be polyurethane. It can have strong adhesion to various substrates, and we have seen that. It's tough and hydrophilic, and so we would like to combine them. And so the approach was a very simple chemistry, where we would have the hydrophobic blocks, the PDMS, and the hydrophilic blocks, and then we could extend these blocks by using chain extenders and we could change this also by using different molecular weights of each of these segments. So let's see what it looks like. And the synthesis is very simple, and we've done it on a lab scale, although the company is actually kind of scaled it up a little bit beyond this. So we would have the precursors, mix it in sequence, some of them together. And then eventually what you would get is dispersions, and so we'd use an anti-solvent water, and you would end up with these dispersive particles or dispersions of these systems. They wanted a water dispersible system. And then we would coat them on fabrics. And this is a dip coating approach, and then we would heat them and dry them. So if you look at the two main components, one is the PDMS and the other is the poly-THF. You can see that as we vary the molecular rate, so this is going molecular rate high in this direction and high in this, the average contact angle on a cotton substrate is reasonably high. It's around 130 to 140. But it just changed depending on the molecular weight we use. If we look at it, if you're going to lower molecular weight, we're going to more hydrophobicity, higher molecular weight here, more hydrophobicity. So what we can do is we can tinker with the hydrophobicity by changing the molecular weight, the ratios, and so forth. The main two components are PDMS and poly-THF, and we can tune the particle sizes as well by playing around with this. So what you find out is that when we get these dispersions, they have multiple size scales, but they usually fall under two to some unsorted ones. You see, you have some smaller, larger, and depending on how you coat them, you can get partial wetting to very little wetting. And these are some of the pictures shown here, where we have gone from pure cotton to applying 2 layers of these coatings using either one type of size or both sides. So let me probe this a little bit more. If you look at it, this is the fabric, and these are the coatings. So the coatings are pretty well absorbed onto the fabric. The contact angle, as I said, is around 130, 140. It packs in well. And so one of the issues is, can we make this even more hydrophobic? Can we make this abrasion resistant? And can we make this so that it's sort of breathable? So what we wanted to do is we wanted to play around with the PDMS PU coating, and also, which has some inherent roughness. We also wanted to see if we can do something beyond just the polymer and block of polymer itself. So one of the ideas we had was to use fumed silica. We have done a lot of work in our lab on fumed silica, so we thought, why not use fumed silica? Fumed silica, branch silica, and it can have hydrophobic or hydrophilic functional groups. So the one we use is hydrophilic or phobic. And so you can see here the water droplets on the fabric. This is pure fabric. As we are adding more silica, you can see that the water droplet becomes more round, suggesting that this is non-wetting it. If you look at the water contact angle, you can see that when we add fumed silica to the polymer, there is some jump, and then it stays stable. So the fumed silica does impart hydrophobicity to cotton. If you do just pure fumed silica, we do get a substantial jump. If you do it with PDMS, PU, we see some increases. And then after a while, if you add a little bit of fumed silica, then it seems to have saturated. We don't see any increase. So we wanted to see if we can modify our coating process to bring this fumed silica into the picture. So we used 2 approaches. One is we just added fumed silica. So we would add fumed silica as a second coat. So the idea would be we would coat it with the polymer or the block of polymer, we would do the fumed silica, and we will look at the properties of this coating. The other approach was actually to integrate the silica in the formulation. And so we would actually do that in the formulation. So we would have not only a block of polymer, but a silica integrated in it. And so that way we could do a single coating, double coating, and we like to see how this works. So we did some airflow measurements using a very crude approach that we have developed in our lab for doing some other things. And what we found was that the pressure drop does go up when we coat it, but it's not too bad considering the atmospheric pressure. So we do have pressure drop changes and an increase, but it is not as bad as you would like. So it is something that's viable and doable. But what is most interesting thing is the abrasion resistance. If you take cotton only, and we have subjected this to Martindale abrasion, and you do 500, 1000, and we haven't gone to 5000, the cotton would just get destroyed. If you just use fumed silica on the coated cotton, that also get destroyed. But then if you have these PDMS PU, either with fumed silica or without fumed silica, we see some nice that we do not see loss of integrity. And so here is some quantitative data. This is just fumed silica on the cotton surface, and then within 500 cycles, that is all gone. If you have the block copolymer with the silica and we add an additional silica, we see that it retains its hydrophobicity. Same thing goes when we have just a block copolymer by itself with the fumed silica as part of the integral part of the formulation. So it seems like it works pretty well from an abrasion resistance standpoint. And we have gone, as I said, as high as 5,000 abrasion cycles and seems to work pretty well. What is happening? What happens is when we have a substrate, we are forming, when we take a formulation, the urethane actually attaches to the cotton, and then we have these hydrophobics, the silica sticking out, which can interact with the fumed silica that we are putting in as a second coat. And so we have hydrophobic interactions, hydrogen bonding on, and they're pretty robust in maintaining the coating. And we have seen that by doing aging tests and weathering tests and so forth. But what is happening when we are doing abrasion? If you have fumed silica, if you do pure cotton, the abrasion just destroys the cotton. When you have fumed silica, you have too many rough fumed silica, which actually gets, when we have the abrader going on, that kind of disintegrates the cotton because it's rubbing against the fumed silica. And even when you have a fumed silica coating, that seems to be not as desirable, but when we have PDMS, PU all together as part of the formulation, that becomes a nicer coating on the fabric, and then we see minimal damage, and this is the one that can show the most abrasive resistance in there. So let me summarize then. So we have developed a coating. It's tunable. We can add fumed silica as part of the coating formulation. It's porous, it's hydrophobic, and it's the best part is its abrasive resistance. And so the companies we have worked with have taken this a step further and have been using that to their advantage in coming up with their own formulation. So let me end here. So I've talked about 3 stories. I've talked about banana paper, natural lignocellulose. I've talked about how banana papers can be used in agriculture, and then we kind of make it a more advanced composite using MOF. And then finally, we talked about fabric coatings, which is not on cotton, but now we have gone from the sustainability to the coatings, which is still sustainable in the sense that it's fluorine-free. And then I have collaborators at various places in Kenya and Benin, in chemistry, plant science, paper science, and students and postdocs have helped me with this project. So let me stop here and try to answer any questions that you may have.
Thank you, Professor Han, for this nice presentation, which is very important from the food safety and crop, increasing the crop efficiency. Is there any question? So first of all, thank you very much for your presentation, for your attendance here. I would very much appreciate. It is an interesting work using banana paper to prevent pesticides or insects. I wonder what is the mechanism behind it. I mean, can you use usual cotton instead of banana, or is there anything special with the banana paper?
Yeah, that's a question that, when we went for funding, that's the first thing they asked us, the Bill and Melinda Gates Foundation, why banana paper? So we have some ideas. So no, if you take other plants, it doesn't work. So we think there are 2 things. First is that the banana fibers have this kind of a tubular structure, which helps in either moisture retention or prevents or helps in keeping the active ingredient there long enough. We've actually done some lab experiments to see what is the binding constants of the active ingredient and what is the release profile. So that's one. The second is the amount of lignin to cellulose is quite unique. I mean, different plants have different, and banana plants have a certain ratio, which works to our advantage in binding the active ingredient to it. So the morphology as well as the chemical composition of the lignin to cellulose is helping us. But it is true that the other plants have been tried, and it doesn't work as well. We've tried things like rose and this and that, and they don't seem to work as well. So that's it has worked. So we stumbled on it. Not that we were clever or anything. We just happened to stumble on it. Then we figured out why it's working. From a standpoint, bananas. So now that we know banana, for example, in Africa, is grown quite a bit, so we can actually use it. And it's grown in other places too. So for example, in Southeast Asia and stuff, so that could be used there as well.
I have this question. Your trial is just for the yam and potatoes. Have you ever tried this banana paper for other crops?
Yes. Yes. So in the US, my colleagues are actually looking at other crops. And also we have our collaborators looking at other crops in Africa. So the technology is, as you can see, is very simple, right? So for a mechanized country like yourself or us, using farmers, a lot of these farming are more mechanized. So the paper wrapping would work only for small farmers. That's why countries like in Southeast Asia or Africa would work well. But it does work well. We can put any kind of actives in the banana, and now we are making not only paper, but we're making other things out of these, so we can think of other matrices being made out of it. So it would work with other active ingredients and for other diseases of the plant. One thing also you can think of is to not just provide kill insects and stuff. You could use it to provide nutrients in a kind of a controlled way as well. So there's some more work going on as well.
Thank you. Thank you very much. Thank you for joining us. Thank you for this nice presentation. Thanks a lot. And
Thank you. Thank you. Thank you. Thank you.
Our third presentation. The topic is improvement of mechanical and thermal properties of graphene, carbon nanotube, and carbon nanofiber reinforced nanocomposites. She is working in the TUSASH, I think, right?
Right.
And we are expecting.
Can you hear my voice?
Yes, we do hear you well. Please, we could start.
Can I?
Yes, please. We are waiting for your presentation.
Okay. Hello, everyone. My name is Merve Özdemir. I'm working in the Turkish aerospace as a quality engineer. Also, I'm a master's student in Gazi University. Today, I will talk about my master's studies influence of mechanical and thermal properties of graphene, carbon nanotube, and carbon nanofiber reinforced nanocomposites. It's my title. In my presentation, I will talk about purpose of the study, carbon-based nanomaterials, nanocomposites, epoxy resin, tler mill, experimental study, characterization tests, experimental results, and finally, general results. In this study, it is aimed to distribute various nanomaterials homogeneously into the epoxy resin using the tler mill and to improve the thermal and mechanical properties of the obtained nanocomposites. In addition, the effects of 3 different nanomaterials used on the nanocomposites will be compared. You can see a lot of carbon. These are graphene, nanotube, tler, diamond, and graphite. Among these, firstly, I will talk about graphene. Graphene is one atom thick, two-dimensional allotrope of carbon. In graphene, carbon atoms are bonded to each other by acid to hybridization in a honeycomb crystal lattice. It is the strong, thinnest, and soft material now. It is 200 times stronger than steel. It can stretch up to 20%. Therefore, it's a flexible material as plastic. It has thermal conductivity and electrical conductivity of copper. It is 100 times the electron mobility of silicon. It is water and gas resistant. It is used in areas such as the separation of gases and its gas-proof feature. In figure 2, you can see the structure of graphene. Also, graphene produces many methods. Some of these methods: exfoliation, chemical vapor deposition, reduction of graphene oxide, and epoxy augmentation. The second one, carbon nanotube. Carbon nanotube can be defined as graphene rolled into the tube shape. CNT structures are also considered one-dimensional structures because they have a very high length diameter ratio. Its properties, it is possible to evaluate the properties of the carbon nanotube as a mixture of properties of diamond and graphite. While CNT is strong and high thermal conductivity like diamond, it is light and flexible like graphite. With its modulus of elasticity over 1 kilopascal and tensile strength of 150 gigapascal, CNT is much higher strength than steel, while it is 5 times lighter. CNT can be produced by various methods. The most important of these methods are arc discharge, laser ablation, and chemical vapor deposition method. You can see CNT's images in figure 3 and 4. The third one and the last one, carbon nanofibers. Carbon nanofibers, one of the most important members of carbon fibers, have been applied as promising materials in many fields, such as energy conversion and storage, reinforced of composites, and self-sensing devices. There are some differences between conventional carbon fibers and carbon nanofibers. The first, but also the most obvious, is their size. Carbon nanofibers have diameters of 50 to 200 nanometers, while conventional carbon fiber has a diameter of several micrometers. Unlike conventional carbon fibers, carbon nanofiber can be prepared mainly by two approaches: catalytically vapor deposition growth and electricity. In the figure 5, you can see the difference between carbon nanofiber and conventional carbon fiber. Nanocomposites. Nanocomposites are multiple solid materials such as nanoparticles, nanofibers, layered nanostructure with one or two dimensions of one phase smaller than 100 nanometers. Mechanical nanocomposites differ from conventional composite materials due to the extraordinarily high surface to volume ratio and or the extraordinarily high aspect ratio to reinforced space. There are three types of nanocomposites. These are polymer-based nanocomposites, ceramic-based nanocomposites, metal-based nanocomposites. Also, nanocomposites produce many methods. Some of these methods are direct mixing, processing the solution, instant polymerization. Epoxy resin, although thermoset polymers have different properties from each other, the most widely used is epoxy resin. Features such as high strength, low viscosity, and low flow rates that ensure good wetting of the fiber during processing and prevent deflection are some of the reasons for the widespread of the epoxy. And tler-on-me, the two or tler-on system uses the shear force generated by the rollers to mix, disperse or homogenize viscose materials. In the tler-on-me, it's possible to obtain homogeneous results with the higher shear stress created by the adjustable rotation speed and the gap between the rollers. Tler-on-me in the figure 6 and working principle of tler-on-me, you can see figure 7. Now we will talk about, I will talk about experimental section. Firstly, materials. In this study, Araldite epoxy resin and Aradus hardener supplied from Hussmann company were used as a matrix material. GMP.
Merve Hanım, we are a little bit behind the schedule. Could we speed up a little bit? We have, I think, 7 more minutes to finalize this speech. So could we speed up a little bit?
Your voice very complex. I can understand.
Could we speed up for this presentation? We have 15 minutes allowed for this presentation, so that 10 minutes passed. So could we speed up a little bit? Bunu biraz hızlandırabilir miyiz diyorum. 15 dakikalık süremiz var ya.
Tabii. In this, you can see the materials is used by study. Nanomaterials, as a nanomaterials, graphene nanopellet, carbon nanotube nanoribbon, and carbon nanofibers were used. In the study, firstly, GMP and CNT nanoribbon were mixed with epoxy resin at doping ratio by using tler-on-me 0 to 0.05 and 0.1, 0.2 and 0.5% by weight. Then carbon nanofiber increases the viscosity of the resin. Carbon nanofiber concentration 0 to 1, 0 to 0.5, 0 to 1, 0 to 2% by weight. Secondly, the resulting resin and nanomaterial mixture using the tler-on-me, hardener was added to homogeneous mixture of phase. Then the mixture, the methanol was degassed under vacuum. Finally, the mixture was cured at 120 degrees centigrade for 4 hours, and samples were produced. You can see 11 samples were produced with different concentrations. GMP figure 9, figure 10, and figure 11. These samples cut in the water jets. Some characterization tests were done on these samples. The characterization tests are 3-point selection tests, SEM analyzers, PGA analyzers, and DSP analyzers. First of all, we can see the 3-point flexural test results. When the test results were examined, the highest flexural strength was observed GMP 0 to 5 sample. In this sample, the flexural strength value increased by 30% compared to the resin flexural strength. When the effect of CNT addition on flexural strength was examined, the flexural strength value of CNT 0 to 0.5 sample increased only 1.35% compared to the resin. It is seen that the flexural strength values decrease as the CNT content increases. This situation reveals that the CNT and the resin not mixed homogeneously enough, and agglomerations occur due to weak interaction between them. This weak interaction was also confirmed by SEM images. Finally, when the effect of CNF addition on flexural strength was examined, it was observed that the flexural strength values increased as the CNF content increased. Now, there is you can see the agglomeration on the CNT as samples. But GMP and CNF samples edit agglomeration compared to CNT edit samples. Now we can examine TGA results. When the TGA results examined, it was seen that the GMP additive increased the decomposition temperature of resin. The highest increase was seen in the GMP 021 sample. However, the addition of CNT and CNF didn't increase the decomposition temperature of the resin much. Last one, DSC results. DSC results, when the DSC results were examined, it was observed that the addition of GMP decreased the glass transition temperature of resin. Similarly, the addition of CNF and CNT decreased the glass transition and TG temperature of resin. Finally, we can talk about general results. When the results are examined in general, it is seen that GMP and CNF additives have a positive effect on the flexural strength of the resin. With the addition of 0.5% GMP and 0.2% CNF, the flexural strength value can be increased up to approximately 30%. This increase indicates that the resin and GMP 0 to 5 and CNF 0 to 2 samples mix homogeneously and there is strong interaction between them. With some SEM analysis, it was revealed that agglomeration occurred more with the contribution of CNT. According to the TGA results, it was observed that the GMP additive increased the thermal stability of the resin. When the results were evaluated in general, it was evaluated that the glass transition temperature TG of the resin decreased with the nanoparticle additive due to lower cross-link densities in the nanocomposite. After the studies are completed, it is expected that the samples that give the most promising results can be combined with carbon fiber reinforced materials and used in the production of composite materials. Thanks for listening.
Merve Hanım, teşekkür ederiz.
Ben teşekkür ederim.
Thank you for this nice presentation. Since we are behind the schedule, we could not take any question. Thanks a lot for joining us again from, I think, Eskişehir. You are in Eskişehir, right? Eskişehir değil mi Merve Hanım?
Gazi Üniversitesi.
Efendim?
Gazi Üniversitesi.
Gazi Üniversitesi. Peki.
Evet.
Ankara'dan katıldığınız için teşekkür ediyoruz. Görüşmek üzere. Bir firma sunumumuz var. Hasan Bey, Aydın Tekstil'den.
Değerli hocalarım, değerli katılımcılar, hepinize iyi akşamlar diliyorum. Aydın Tekstil tanıtımını yapmak üzere huzurunuzayım. Aydın Tekstil bir aile şirketi. Grubumuzun 4 fabrikası var. Aydın Tekstil 60 yılı aşkın tecrübesi olan bir firma. 90 üzeri ülkeye ihracat yapan, 2500 üstü çalışanı olan bir grup. Grubumuzun kilometre taşlarına gelince, Aydın Tekstil 1957 yılında kuruldu. 1989 yılında şu anda merkez fabrikamızın olduğu iki telli organize fabrikamızda kurduk. Orada üretime başladık. Şu an 80 bin metrekare kapalı alanı olan bir fabrika. Grup ikinci fabrikasını 2006 yılında Sakarya'da Aydın Endüstri Nova Sünger olarak kurdu. Buranın da kapalı alan metrekaresi 55 bin metrekare. 2014 yılında üçüncü fabrikamızı yine Sakarya'da başka bir lokasyonda kurduk. 25 bin metrekare kapalı alan olan bir fabrika. Sayfa herhalde almadı. Dördüncü fabrikamızda Kayseri'de 2016 yılında üretimi alarak 4 fabrikaya ulaşmış oldu. Grup şirketlerimiz tekstil olarak Aydın Tekstil İstanbul, Sakarya, Kayseri. Onun dışında Aydın Endüstri'de mobilya, yatak yapımı ile ilgili üretimlerimiz var. Ayrıca çeliktel üretiyoruz. Hijyen grubumuz var. Kimyasal uygulamalarımız var. Sünger üretimimiz var. Burada yine grup fabrikaları ile ilgili, tekstil fabrikaları ile ilgili, 3 tekstil fabrikasının lokasyon ve metrekarede ve işçi bilgileri var. İstanbul fabrikamızda 1200 çalışanımız var. 8500 ton yıllık iplik üretimi, 3500 ton yıllık yine boya kapasitesi ve 5500 ton da kumaş boya kapasitemiz var İstanbul'da. Kayseri'de yine 450 60 dokuma makinesi, 60 örme makinesi ve 100 bin metre gün üretimi olan yaklaşık 2,5 milyon metre yıllık aylık üretimi olan bir fabrika. Sakarya fabrikamız yine 450 civarında çalışanı olan, grubun toplam çalışanı 2500, bunu söylemiştik zaten. Kadife üretimi İstanbul Merkez Fabrikamızda kadife üretimi yapıyoruz. 81 makineyle Avrupa'nın ve Türkiye'nin en büyük üreticilerinden biriyiz. Yaklaşık 20 bin metre günde 6 milyon metre yıl olmak üzere bir kapasitemiz var. Yine Sakarya'da çözgülü örme, Rashid üretimimiz var. 16 makinamız. 45 bin metre gün ve 3,5 milyon metre yıllık bir üretim kapasitemiz var. Kayseri'de örme ve dokuma olmak üzere metal yani yatak kumaşı üretiyoruz. Orada da yine 60 dokuma ve 120 örme olmak üzere 180 makinemiz var. Orada da yaklaşık olarak dokumada 18 milyon metre yıl, örmede de 35 milyon metre yıl olmak üzere bir üretim kapasitemiz var. Finish kabiliyetlerimizle ilgili de işte basic kaplama uygulamaları, kular uygulamaları, FR uygulamaları, kalender, laminasyon, fırça, yine şardon, baskı, RAM uygulamalarımız gibi pek çok entegre tesislerde bulunan bütün finishing makinelerine sahibiz. Evet. Ne anlatayım isterseniz? Aydın Tekstil dediğim gibi 4 fabrikası olan döşemeli kumaş ve yatak kumaşı üreten bir grup. 3 tane tekstil fabrikası olan Kayseri, Sakarya, İstanbul'da olan bir grup. Kapasitelerimizle ilgili dediğim gibi Avrupa ve Türkiye'nin en büyük kapasitelere sahip 3 tane büyük firmalarından biriyiz. İstanbul fabrikamızda iplik üretimimiz var. İplik şönil üretiyoruz. Fantazi iplik üretimimiz var. Hava tekstürüde üretiyoruz. Ayrıca polipropilen iplik üretimimiz var. Polyester büküm üretimimiz var. Kamgarn hattımız var. Ee, 2017 yılında İstanbul Merkez Fabrikamız Ar-Ge merkezi oldu. Akabinde Aydın Endüstri Fabrikamız ve en sonunda Kayseri Fabrikamız Ar-Ge merkezi oldu. Şu an grubun 4 fabrikasının içinde Ar-Ge merkezi var. Yılda 3000'e yakın desen yapıyoruz. 1035 müşteri talebi karşılıyoruz. Yılda 18 tane fuara katılıyoruz. Ulusal ve uluslararası. Yaklaşık Ar-Ge merkezinde de 18 tane Ar-Ge merkezi personelimiz var. Bu arada Ar-Ge merkezlerimiz 5 tane 1501 projesi, İstanbul Merkez Ar-Ge merkezinin 5 adet kabul görmüş 1501 projesi var tamamlanan. Şu an Kayseri Ar-Ge merkezimizde yine bir adet kabul gören ve devam etmekte olan 1505 projemiz var. Üniversite işbirliklerimiz devam ediyor. Bu arada Avrupa Birliği projesine fokuslanmış durumdayız. Şu anda onun üzerinde çalışıyoruz. Sürdürülebilirlik ve sürdürülebilirlikle ilgili bir takım çalışmalarımız var. Recycle, ham madde kullanımı ve recycle kumaş üretimine yönelik çalışmalarımız var. Devam edelim. Sürdürülebilirlikle ilgili enerji tüketimini azaltmaya yönelik ve karbon ayak izi, su ayak izini düşürmeye yönelik çalışmalarımız var. Dediğim gibi enerji ve su tüketimini azaltmaya yönelik iç kaynak projelerimiz devam ediyor. Uluslararası geçerli olan ve önemli sertifikaların hemen hepsine sahibiz. Bunlardan birkaçını ekranda görebilirsiniz. İlgili marka bilinirliği ile ilgili de son dönemde Superhydrophobic belgesi olan bir firmayız biz. Superhydrophobic bildiğiniz gibi devlet destekli tek marka desteği veren program. Denetlemesinden geçerek marka desteğini aldık. Şu anda marka desteği sayesinde 4 fabrikamız ortak ERP sistemini değiştirerek ortak ERP sistemine geçtiler. Bunun dışında uluslararası ajans ve ajansalardan marka bilimlerini arttırıp ihracatımızı arttırmaya yönelik olarak çalışmalarımız devam ediyor. Yaklaşık 110-120 milyon dolar civarı tekstil ihracatı gerçekleştirdik bu sene. Hedefimiz önümüzdeki yıl en azından 150 milyon dolarlara çekmek. Dediğim gibi üniversite işbirliklerimizi devam ettirme, marka bilinirliğimizi arttırmaya yönelik çalışmalarımız sürüyor. Kısaca söyleyeyim.
Teşekkür ediyorum dinlediğiniz için.
Dr. Rashid, do you hear us? Dr. Rashid, do you hear us?
Hi, good afternoon.
Hi, good afternoon. Now you join us. Okay, the next presentation is the effect of carbon fiber reinforcement on dimensional variations of 3D printed polyamide composites, a simulation study. We are behind the schedule, so I'll be pleased if you could speed up your presentation and finalize it in 10 minutes, I hope.
Sure, sure. Please allow me to share the screen.
Yes. Yes.
Yes, can you see it?
Yes. Okay, fine. You follow it? Do you follow it?
Yes.
Yes, please, we are listening you.
Okay, thank you so much for this opportunity for talk here. My name is Rashid. I'm a PhD student at HBKU, and today I will be presenting some portion of my research work. To complete in time, I will skip this outline, but the main research vision for our research group, we are currently working on the simulation computational modeling for 3D printing process, more specifically for polymer composites. So there are a few factors which needs to be considered, which is the material we are using, the product, the design of the product we want to fabricate, and the process itself, its parameters. So in order to fully understand and predict the performance of the 3D printed structures, it is very important to understand these interlinked parameters. I will not go into the applications and motivation behind the studies for polymer composites, because the speakers and other participants have already discussed a lot about it. But in general, I would say the polymer composites, if we look into the material property corner here up of the triangle, we have plenty of options in terms of the polymers itself and the reinforcement, which could be particles, short fibers, or continuous fibers. If we consider the material base itself and the reinforcement content, we have we can end up with an infinite number of options for the polymer composites. Secondly, 3D printing process is relatively cheaper process, specifically if we talk about FDM process. Now it's readily available, it's rapid, efficient. But if we consider the process variations itself, and also considering the possibilities of synthesizing the polymer composites, we can end up with an infinite number of options, which is not possible with the normally used experimental approaches. So the best motivation behind this is to move towards finite element analysis tools for the performance prediction and optimization of the 3D printed polymer composites. A little background, FDM process itself is a complex process in which different heat transfer phenomena are occurring, where first of all material is heated within the nozzle, then it extrudes through the nozzle, and it goes into the print bed. Once it is deposited onto the bed, it cools down. So it's a thermal cycling going on. Once the one layer is deposited, when another layer is built upon the other layer, it again heat up to some extent. So you see there are temperature variations within this, and we have to consider all these phenomena to accurately predict the performance of the 3D printing process itself. So there are a few studies in the literature regarding the flow behavior within the nozzle, the orientation of the fibers in case of short fibers within the nozzle, then the solidification of the beads, and ultimately when the print is done, the residual stresses and warpages comes into the action. So based on this literature, there are a few research gaps which needs to be addressed. Like we have to come up with the integrated models to consider all these aspects, the validation of these models, and then generalized model which can be adopted for any material. So our goal is to model the 3D printing process for polymer composites. We are mainly focusing two main softwares, Digimat and Abacus, where we can perform the multi-scale process simulations. We can predict the residual stresses and distortion, and ultimately we can also predict the mechanical response of the material once it goes into the application. This project or this research will provide a characterization understanding of different interlinked parameters, which is material property, design, and process, the guidelines for design for additive manufacturing, multi-scale modeling of the fused filament fabrication process, and ultimately the accurate thermomechanical characterization. In this way, we can have a significant cost savings in terms of material energy. We can lower the research and development cycle time and cost. And finally, we can have inexpensive, rapid, and easier workflow for precise and reliable predictions. In the work I'm going to present, we used carbon fiber reinforced polyamide 6 composites, where we varied the carbon fiber reinforcement from 10 to 28% to observe the deflections, warpages, and residual stresses. We selected a simple model, which is ASTM D638, a tensile specimen, modeled using the SolidWorks software, which is sliced using the slicing software, and then it is imported into the software, where we have to define the process itself, the printer specification, the kind of analysis, the geometry, and material properties. And ultimately, we have to define the manufacturing steps and simulation. Ultimately, we can have after the simulation is complete, we can extract the warpages and residual stresses information. Here, I'm comparing just two, where one is pure polyamide 6, and other one is the polyamide 6 reinforced with 28% carbon fiber. Once the printing is done, after the cooling, we can observe that the deflections of the final part, which is very important to study once when you have to print the functional components, the control over the dimensions is very important. So by adding the carbon fibers up to 28%, we can reduce the deflections of the 3D printed specimen from 4.5 millimeters to around 3 millimeters. Secondly, if we look into the residual stresses, it gives the opposite response. It increased a little bit as compared to the case of the pure polyamide 6, but this is due to the reason that carbon fiber inhibit the contraction of the material. It inhibits the shrinkage of the material, due to which the dimensional variations are caused. So if we look in this graphical form, you can easily see that the materials, the deflections for the pure polyamide 6, where no carbon fiber was used, we have a maximum deflection from the design values. But increasing the carbon fiber reinforcement, you can significantly reduce these deflections. And ultimately, if you look at the right, the warpages can also be significantly reduced. But it causes the Farn-Mises stresses, which we also say the residual stresses, to increase a little bit as compared to the pure carbon fiber reinforced composites. So in conclusion, we can say a significant impact of carbon fiber reinforcement was observed on the deflections, warpages, and residual stresses. The carbon fiber reinforcements significantly improved the 3D printing manufacturing performance of these composites. The deflection values drops with increased carbon fiber reinforcement. However, residual stresses increase as we saw. This is due to the reason that the carbon fiber reinforcement hinders the shrinkage of the material during the cooling phase. In future, we are also considering to compare these results with the experiments to validate the simulations and to improve it further, and also to study the effect of process parameters to optimize the print quality further. Thank you so much.
Thank you for your presentation, and you speed up very well. Thanks a lot. Thank you for joining us from, I think you are in Pakistan right now. No,
I'm in Qatar.
You are in Qatar, okay. Thank you for joining us from Qatar and for your presentation. Thanks a lot. Okay, our next presentation is from Seda, Bekin, Açar, preparation of Halloysite, Nanotube-Tertiary, Amine, Thermoset Nanocomposites via free radical Photocrosslinking Polymerization. Seda Hanım, duyuyor musunuz?
Evet hocam, duyuyorum. Merhaba.
Merhabalar. Seda Hanım, sizin ikini de biraz hızlandırabilsek çok memnun olurum. 10 dakika.
Tabii.
Eğer mümkün olursa bayağı bir geri kaldık. Programın bayağı bir gerisindeyiz.
Tamamdır hocam, merak etmeyin. Kontrol edeceğim. Tamam mı hocam? Ekran paylaşımı yaptım.
Görüyoruz. Başlayabiliriz lütfen.
Hi everyone, I am Seda Bekin Açar. I work as a research assistant at Yalova University, Department of Polymer and Materials Engineering. Thank you for giving me the opportunity to present. Dear participants, welcome to my presentation again, titled Preparation of Halloysite Nanotube-Tertiary Amine Thermoset Nanocomposites via Free Radical Photocrosslinking Polymerization. The outline includes introduction and purpose, materials and methods, results and discussion, and conclusions. So, first of all, in the present study, naturally available halloysite nanotubes were first modified by 4-dimethylaminobenzoic acid and then used as nanofiller by varying weight from 0 to 8% in a mixture of multifunctional methacrylate monomers. Free radical photocrosslinking of this mixture enabled the in-situ preparation of functional halloysite thermoset nanocomposites. The main purpose of this study is to prepare thermoset nanocomposites containing halloysite known as natural nanotubes with UV light curing systems. The chemical materials that are used in the study are as follows: halloysite as nanofiller, 4-dimethylaminobenzoic acid as silylation agent, triethylene glycol dimethacrylate as monomer, bisphenol A glycerolate dimethacrylate as monomer, benzophenone as photoinitiator, and toluene as solvent. Halloysite is a natural nanostructured tubular silica alumina clay. It consists of rolled kaolinite layers with a silicone-like outer surface and an aluminum-like structure inside the tube. Indeed, halloysite particles are readily available and much economical compared to their analogs, such as carbon nanotubes. Based on their unique properties, such as natural abundance, biocompatibility, low density, large aspect ratio, and mechanical strength, the halloysite have been appeared as a suitable candidate as nanofiller both thermoplastics and thermosets. To synthesize halloysite tertiary amine, halloysite was modified with 4-dimethylaminobenzoic acid. For these first 2 grams of halloysite were dispersed in 50 milliliters of toluene under ultrasound. Then the solution was purged with nitrogen for 15 minutes. Subsequently, 0.01 moles for dimethylaminobenzoic acid was added to the mixture and degassed again with nitrogen. And then it was mixed in a magnetic stirrer for 18 hours at 110 degrees Celsius. The final mixture was then cooled at room temperature, filtered, and washed with toluene for several times. Thus, a halloysite tertiary amine nanofiller was obtained by filtration and draining the solid phase. The structure of this functional nanofiller is as shown in the figure. Thermoset nanocomposites containing functional halloysite were prepared by free radical photopolymerization of multifunctional methacrylate monomers with benzophenone photoinitiator in the presence of halloysite tertiary amine. You can see the final structure in the figure. For this purpose, multifunctional methacrylate monomer pair were placed in a flask and mixed to obtain a homogeneous solution via vortex and ultrasonication. Tertiary amine modified halloysite was added to the mixture at 1, 2, 4, or 8% by weight and homogeneously distributed by the help of vortex and ultrasonication. Benzophenone was added to the solution mixture and thermoset nanocomposites were obtained by photoreactor with 16 lamps emitting at 300 to 400 nanometers at room temperature. Final nanocomposites were dried in a vacuum oven at 40 degrees Celsius for 12 hours, and all other polymerizations were performed under identical experimental conditions, and the resulting nanocomposites are as shown in the figure. After the halloysite tertiary amine was synthesized, the success of the functionalization was confirmed by Fourier-transformed infrared spectroscopy. According to this, aromatic CH, carbonyl, and aromatic CC peaks were observed in the spectrum of functional nanofiller. In addition, Fourier-transformed infrared spectroscopy was also performed for the thermoset nanocomposite. So, in the FTIR spectrum of the thermoset polymer, the observation of the CH and the CO bonds were evidence of the successful synthesis of thermoset nanocomposites. Neat thermosets and thermoset nanocomposites containing different weights of halloysite were also investigated in terms of mechanical properties. Based on the tensile test results, the tensile strength, elastic modulus, and percent elongation values of all halloysite tertiary amine nanocomposites were higher than those of the neat thermoset polymer. As can be seen from the table, adding of 4% of modified halloysite into thermoset polymer matrix increased its tensile strength by 2.9 times, elastic modulus by 1.9 times, and elongation at break by 1.3 times compared to neat thermoset respectively. So we can say that halloysite tertiary amine nanofiller increased the mechanical properties of the nanocomposites. At the end of the study, we can reach the following conclusions. Halloysite tertiary amine thermoset nanocomposites were successfully prepared by in situ free radical photocrosslinking polymerization of multifunctional metal plates. The covalent bonding of halloysite tertiary amine with thermoset networks was confirmed by FTIR spectroscopy. The final nanocomposites demonstrated higher mechanical properties rather than neat thermoset polymer. Tensile strength in pure thermoset polymer was 5.51 megapascals, whereas in thermoset nanocomposites containing 4% halloysite tertiary amine, tensile strength increased up to 15.96 megapascals. After higher loading ratio, the mechanical properties of decreased due to possible agglomerations. In the following period, the obtained nanocomposites should also be evaluated in terms of thermal properties. In addition, different functional groups and modification methods can be determined. We offer our gratitude to the Scientific and Technological Research Council of Turkey for their support. Also, as you can see in the first two references, we have studies on thermoset nanocomposites prepared with halloysite nanofillers containing different functional groups. Thank you for your attention.
Thank you for this nice presentation. Seda Hanım, zamanında da bitirdiğiniz için ekstradan teşekkür ediyoruz. Bugün programın biraz gerisinde kaldık.
Ben teşekkür ediyorum hocam.
Bunun için çok teşekkür ederiz. Yarın da devam edecek değil mi? Yarın saat 9'da tekrardan bu son presentation'da. Yarın görüşmek üzere diyeyim. Çok teşekkür ederiz. Sağ olun.